Hi, in this segment I want to talk about series and parallel capacitors. We already talked about series and parallel relationships. Recall that two components are in series if they have the same current flowing through them, and that two components are in parallel if they have the same potential applied across them. And we've talked about the rules for combining resistors in series and resistors in parallel. What I want to do here is talk about the rules for combining capacitors in series and capacitors in parallel. So recall that a capacitor is just two conductors separated by an insulating layer. And typically in this class, of course, we talk about the parallel plate capacitor, but in real life, there's a number of different designs for capacitors. When the capacitor is connected to the battery, charge will flow from the battery and charging up the capacitor. We already knew that, right? And charge will flow for how long? Well, charge will flow until the potential across the capacitor is equal to the potential across the battery. And if we think about this, we can almost see it as like a competing potentials, right? Because the battery here is trying to push the current in a clockwise sense, and the capacitor is trying to push current in a counterclockwise sense, right? And so if I was to initially hook up this battery to an uncharged capacitor, well, then the battery would win, and the current would flow in a clockwise sense until the capacitor charged up. And once those two are sort of equal, then the current stops flowing. Okay, so for this segment, we're going to talk about after that current stops flowing, right? Once the capacitor is totally charged up, what is the situation? In the next segment, we'll include some equations for the time-varying nature of the charge on a capacitor. So we'll save that for the next section, though. For right now, we're talking about capacitors that are all the way charged up. So here's a little schematic to show how a parallel and a series circuit might look differently. Here we see the parallel circuit. Notice that the potential is the same across each of these capacitors, right? Remember that elements that are in parallel always have the same potential across them. So the potential across C1 is the same as the potential across C2 is the same as the potential across C3, Notice that in series capacitors, that's not true. They don't necessarily have the same potential across them. However, notice that if any current went through one of these, it would have to go through each of them. Again, series elements share the same current. Parallel elements share the same potential. Let's focus on the parallel circuit for a moment. In the parallel circuit, again, the potential is the same across both of these. And so we could set that potential equal to each other and do a little algebra. I will spare you the details. Suffice to say that parallel capacitors add regular. However many capacitors you have in parallel, you simply add the capacitances of all of them, and that gives you the equivalent capacitance of that we could replace those two with and get the same exact value. Get the same behavior out of the circuit, right? It tells us how we could swap out two or more capacitors with one capacitor and have the exact same behavior. Store the same amount of energy, store the same amount of charge. All of those things could be exactly the same if we swapped out two or more capacitors with one equivalent capacitor. And so for parallel capacitors, they just add regular. Do notice that this is the opposite of resistors. Remember that for resistors, it is series elements that add regular, and parallel elements add reciprocally. So series capacitors, they can be a little bit tricky. Remember, in a series circuit, the same current flows through every element. They all share the same current. We believe that because there's no junction in between series elements, and we also believe in the conservation of current, which says that current does not disappear. So that means the same current in this capacitor as in this capacitor while we were charging it up. Think about what that means. That means that whatever charge flowed into this capacitor also flowed into this capacitor. That means that the charge on series capacitors is always the same. There's another way to look at that. Let me redraw this on the board. So here's this same circuit, and I've drawn it on the board here. And what I want to do, though, is I want to point something out. And that is that remember that a capacitor is always two conductors separated by an insulator. That means that this is an insulator, and that's an insulator. Notice then, is this little chunk of the circuit actually connected to the battery? Is that little eye shape actually connected to the battery? It's not, which is super weird, kind of, since we're calling it a circuit. But look, this part right here, this is a conductor. It is connected to the positive part of the battery. This part down here is a conductor. It is connected to the negative side of the battery. But there is an insulator on either side of this little eye. That means that this is neutral. Okay, so this is another way of looking at why the charge on series capacitors always has to be the same. Because charges on a capacitor, like the charge on the two plates of the capacitor, are always equal and opposite. That means that if I have plus Q here, I have minus Q here. Right? That's just what capacitors do. We've known that for a couple chapters. They store equal and opposite charges. Well, if this chunk right here is going to be electrically neutral, if we have minus Q on this plate, well, we absolutely must have plus Q on this plate. And again, we've known for several chapters that capacitors have equal and opposite charges on them, on the two plates. Therefore, if this is plus Q, this is minus Q. And we have to conclude that series capacitors always have the same charge. That is a fact, a memorized fact. I mean, we arrived at it logically, but you don't want to have to go through these steps of logic every single time you look at series capacitors. So I would say that this goes in the category of just memorized facts. Just if we can remember that series capacitors have the same charge, it will make solving problems involving capacitors a little bit easier. And we can use this fact to come up with the rules for adding capacitors in series. And again, I will spare you all of the algebraic details. Suffice to say that capacitors in series add reciprocally. So notice that the rules are flipped, right? Series resistors add regular. Series capacitors add reciprocally. Parallel resistors add reciprocally. Parallel capacitors add regular. So it's a little bit tricky. The rules are just backwards. All right, let's practice this just a little bit. Which of the following combinations of capacitors has the highest capacitance? Well, let's go ahead and I'm going to pause the video and want you to think through this. I'll see you on the other side. Okay, so I think that, we could just assign a value to each of these and go through and crank out numbers and then compare them. That would certainly be one way to do it. But I want to approach it more from sort of a conceptual perspective. Using those equations, we can arrive at the fact that two series capacitors always have an equivalent capacitance that's less than either of the individual capacitances. And two parallel capacitors always have a C equivalent that is greater than the individual capacitances. Notice that we already reached this conclusion about resistors, but flipped, right? We said that two series resistors always has an equivalent resistance greater than the individual two resistors, and two parallel resistors always have a combined resistance that's less than the two parallel resistances, which sometimes is a little bit tricky for students. Here the rules are opposite. So two series capacitors have a CEQ that's less than either of the individual Cs, and the parallel capacitors have a CEQ that is greater than the individual Cs. So let's go through these and see what we get. And they're all identical capacitors. Let's just let them all have value C. Let's say they all have value C. And so that means that the equivalent capacitance of A, well, that one's easy. C equivalent is equal to just C. How about B? Well, for B, what can we say? We know that two parallel capacitors always have an equivalent capacitance that's greater than the individuals. So we know that this is greater than C. It turns out it's going to be exactly 2C, but that's all right. We'll just roll with this for now. Option C, not to be confused with capacitor C. For option C, the C equivalent is what? Well, those are in series. So that will be less than C. How about D? D is kind of a tricky one. Notice on D, we have two parallel capacitors that are in series with another capacitor. So in other words, this capacitor, value C, is in series with these capacitors, combined value 2C. Well, we know that series capacitors series capacitors have an equivalent capacitance that's less than either of the series elements. That means that the equivalent capacitance of D is less than C or 2C. Well, if you're less than C, you're definitely less than 2C, and that means here, again, C equivalent is less than C. Well, can we rank them now? Or pick out the biggest at any rate? We've got an equivalent of C, let's see, greater than C, less than C, and less than C. Well, it must be greater than C. Option B, and indeed. Okay, let's do a numerical example. Okay, so the first question here, find the equivalent capacitance of the combination of capacitors in the circuit. Much like we did with resistors, we really have to start with, we have to find a pure relationship in here and start there. There's really only one place we can start, and that is with the 5 and the 1. Notice that the 5 and the 1 are in parallel. Notice that the 5 and the 3 are neither parallel nor series. They do not have the same potential across them, and they also do not have the same current through them, guaranteed. In other words, there is a junction in between them. So they are not in series, and they don't have the same potential across them, so they're also not in parallel. So we cannot start by combining those two. Similarly, we cannot start by combining those two. We have to start by combining those two. Now, parallel capacitors simply add. I'm pretty good at adding 1 and 5. 1 plus 5 is 6. So now our simplified version of our circuit looks like this. I've reduced my 5 and my 1 to a single 6. Now notice that we have two series capacitors. Series capacitors add reciprocally, and so we would have CEQ equals 1 over 3 microfarads plus 1 over 6 microfarads inverse. Run our calculator. We get 2 microfarads. And so now our simplified version of our circuit looks like this. And finally, we are ready to answer part A. Part A says find the equivalent capacitance. It is 2 microfarads. How about part B? What charge flows through the battery as the capacitors are being charged? Well, this is the equivalent capacitance, right? So the circuit will behave the exact same with just a single one of these as it would with all 3 of these. So if we want to know what the total charge flowing out of the battery, the total charge flowing out of the battery will be the same in this situation as it is in this situation. So why solve that? That's hard. Let's solve this. This is easy. Q equals C times delta V. That's 2 microfarads times the voltage across it, which is 12 volts. Okay, so now we have found the charge on this capacitor here, and that is 24 microcoulombs. And that is the charge that flowed out of the battery. So now let's look at C. C says, what is the charge that is stored on the 1 microfarad capacitor? Well, in order to do that, we need to look back at this circuit here, because we sort of eliminated the 1 microfarad capacitor from this, right? We claimed that 24 microcoulombs flowed out of the battery. So 24 microcoulombs flowed out of the battery. Where did it go? Well, it got deposited on this capacitor. So a lot of folks might say, oh, if I want to know the charge on this capacitor, what will I do? Ooh, that's an easy equation. I would just do C times V. You got to be careful with that, right? It's not 3 times 12 is 36 microcoulombs. Why? Because there's not 12 volts across this capacitor, right? We have some voltage across this element and some voltage across this element. Together, those add to 12 volts. So there's not 12 volts across this capacitor. In order to figure out the charge on this capacitor, I'm going to first find the voltage across this capacitor. In order to do that, I need to know what charge is on it. We actually already know what charge is on it, because 24 microcoulombs flowed out of the battery. Where did it go? It went right here. Why didn't it get distributed through all of this? Remember, this right here in between these two conductors, this is an insulator. So no charge can pass. Therefore, if 24 microcoulombs went out of the battery, we have 24 microcoulombs there, negative 24 microcoulombs right there, and the voltage across that element, we're going to use this equation right here. Delta V equals Q over C equals 24 microcoulombs divided by 3 microfarads equals 8 volts. Okay, so we're almost there now. We're almost there now. So we know that everywhere here is at 12 volts. Everywhere here is 12. And we just calculated that we have a voltage drop of 8 volts across this capacitor. Well, if I'm at 12 volts there, then everywhere here must be at 12 minus 8 is 4 volts. Of course, the negative side of the battery is at 0 volts. So, what is the potential across my 1 microfarad capacitor? It is 4 volts. Now, I am ready to calculate C. So, question C says, what is the charge on the 1 microfarad capacitor? We're ready to answer that now. We can say that Q equals C times V. C is 1 microfarad. V is 4 volts. We get 4 microcoulombs. Okay? So, here is our answer to part A. Here is our answer to part B. And here is our answer to part C. A little bit tricky. Notice if it had asked us for the charge here, we could simply calculate it. It would be 4 volts times 5 microfarads, 20 microcoulombs. Notice that this rule that we observed earlier, even though we didn't explicitly use it, it has happened here, right? Remember that the charge on series capacitors is always the same. Here we have a total of 24 microcoulombs on this capacitor, and here we have 20 microcoulombs here, and 4 microcoulombs here, a total of 24 across these two. Two series elements have the same charge. So these can be a little bit tricky, and I think the tricky part is people see equations like this. It's only 3 elements, and they think, oh, that's easy, I can multiply 2 things together. It's what 2 things do you multiply together? That's the tricky part. And you have to be very systematic about this to reach the end and get the correct answer. Right? You have to be very step-by-step, very systematic, like we have done here. Now, there's other ways to solve this. I think this is the most intuitively satisfying and the less... this relies less on sort of memorized rules and more on just kind of plugging away and figuring it out than maybe some other strategies. So.